welcome everyone. Welcome to this new session of Evolve webinar. So today for this session, we are going to talk about storage technologies and specifically in the framework of HPC and container enhanced systems. So it's not only HPC, traditional HPC, but we have also a lot of materials today about Kubernetes and container. So today we have three different speakers to address the various aspects of the storage technologies on Kubernetes. So myself from DDN, Per Simonson, the CEO of MemoScale, and Sri Kumar from IBM Research. So the three speakers mostly will have the same amount of time. So you will have three different talks. However, as described in this outline, we have 1 hour, 3 times 15 minutes. But for the question, please use the Q&A tab or the chat, and we will collect all the questions during the webinar, and we will walk through the question at the end of the three sessions. So we will have one session dedicated to the Q&A for 10 minutes, mostly speaking, 45 minutes after the beginning of this talk. And depending on the question, the most relevant speaker will pick up and try to answer this best. So in more detail for the three contributions today, so myself, I will introduce what we have built in Evolve in terms of storage architecture and all the heterogeneity that we have here on the difficulties to address performance monitoring in a convenient way. Then Per will present the Erasure coding in order to improve the fault tolerance of the system, and also a S3 gateway which has been developed during the project, which considerably increase the data capacities of the platform. On Datashim from Sri Kumar, who is going to show how a container can be agnostic from the dataset location. After this three talk, so again, we have this consolidated Q&A session, and then we have a small wrap-up just to mention that there is other seminars, and if there is maybe a bit of time left, we can address additional questions. So just a quick introduction, what is Evolve by itself? So Evolve, it's a heterogeneous platform. So the H2020 project was really funded with this idea of pushing the borders of what is heterogeneity in HPC. So a few years ago, all the systems were kind of homogeneous, but now I will say the norm has evolved. You can see on the left side of this slide, what is in Evolve, it's a bit extreme, but what is a normal HPC system nowadays. So these yellow bricks are the compute resources, so basically compute server with 1 or 2 CPUs. On some of these yellow bricks has been augmented. For instance, here you see on the extreme left, they got like a small storage silo. So physically, it means that there is NVMe device, a flash device connected to the PCI bus of the system, so the CPU can directly address the storage resource. Some other has been extended in terms of processing resources. So on the top, you have this yellow brick plus the large green thing, which is a GPU, or at the bottom, more specialized, again, the CPU, the yellow brick, but the server also is hosting a FPGA. So this is really heterogeneity from a compute perspective. And this is bringing a lot of new questions, challenges that we have addressed in Evolve. So typically in terms of resource allocation, how do you allocate resource when not all the resources are homogeneous? But today our focus is more specifically on the storage side. And on the storage in Evolve, we have also heterogeneity. So here we see that we have a 2-level storage. There is this DDN brick at the center, which is a full flash server. And then on the right, this is a cluster, so parallel file system based on the hard drive. So now we are going to detail a bit more the heterogeneity at the storage level and how do we observe performance into this. So heterogeneity is storage. So from a technology standpoint, this is well known. So there is a whole pyramid of technologies available for storage architecture. At the very bottom, the cheapest in terms of dollar per gigabyte, this is a magnetic tape. So very high capacity, very nice feature because you have this 0-watt persistent storage. So you store data and it's not costing anything on the electricity bill. But in terms of performance, this is maybe not superb. So above this, you have the magnetic device still, but no, this is hard drive, so rotating device. This is the most used technology in the storage system currently, I mean, in the world, in terms of shipment. Very convenient, very well-known technology. However, since this is a mechanical rotating device, in terms of latency, it's lagging a bit behind the newer systems such as the SSDs. So SSDs is based on flash, so it's much faster. It's also more expensive. And then we have an increased latency and the decreased bandwidth. So this is perfect. And on the very top of this pyramid, you have the persistent memory. So Optane from Intel is one of them. And here the price is even higher, but the performance is even better, close to the one from DRAM. So this whole pyramid can be used by the storage architect. And furthermore, for the architecture, the same technology can also deliver different performance and different criteria. So one of them, speaking about fault tolerance, is a device, so it could be a hard drive or a flash device, and NVMe is single or dual ported. When a device is dual ported, it means that two servers can access the same device. So if one of the servers dies, then the other server can still access the data. At the opposite, for a single ported device, the device is connected to a single server. If the server fails, then you cannot access the data anymore. So obviously, dual ported systems are much better for fault tolerance. However, they are also higher grade or more expensive. Here we are leveraging some technologies developed by MemoScale, so a very fast Erasure coding library, which is going to allow us to use single ported device and still keep an extreme level of fault tolerance. So I've already touched a bit this point about this local device. So for fault tolerance, if we have a device locally within the compute node, it's much better in terms of latency because we only have to cross the PCI bus, no need to go through the network. However, if the server is lost, so if the compute node is lost, not only we are reducing our computing capabilities because one server is out, but furthermore, we are losing access to the data. So this is one of the drawbacks of local device. And the other architecture is to use remote device. So at the price of an increased latency, then we can disaggregate the system and centralize everything and apply fault tolerance. There is several protocols in order to implement this remote access, iSCSI, NVMe over Fabrics, or also some proprietary system software developed mostly on RPC, and this is what we are doing in Evolve. On another point, in terms of heterogeneity, which is a bit less obvious, is that within a same system in production, we can have multiple generations, at least two generations of storage device. So for instance, if part of the system receives a technological upgrade, then typically we will receive a higher capacity and higher performance device. So much better latest generation of NVMe, PCI Gen 4 or things like that. So it means that in terms of storage architecture, we need to be able to individualize this storage device. So depending on the performance, when we do the load balancing, when we dispatch the I/O workload on the system, we need to care about the individual performance of each device. So we are sure that this device will receive the fraction of a workload, which is in accordance with the fraction of the total performance. And this is a difficult point that we have been able to address in Evolve as well. So now the main heterogeneity in Evolve, it's a bit disruptive, has been introduced by this infinite memory engine. So this is a flash layer that we have introduced between the Lustre hard drive based system on the compute node. So there is eight, if I remember correctly, eight full flash server. Each server is hosting 24 flash device. And all these data are managed by the IME software, and it performs as a transparent cache. So it means that the compute node will be able to push their data, to write data to the flash transparently. They don't know that they write to the flash, but the data movement is intercepted by the IME. And then at the end, data are moved automatically to the Lustre. So the interest here is that Because this is flash-based, the system is able to handle much more aggressive I/O pattern than usual. So typically, small I/O requests or internally I/O requests are very difficult for a traditional parallel file system to cope with. But when it's flash, it's much easier because, of course, the substrate is different. So IME allows basically to address all this complicated workload and then move the data in a much more convenient way, streamline sequential access to the storage system based on Lustre. So it means that in terms of performance monitoring, we have now two layers to observe Lustre, to know what's going on at the hardware level, and also IME. When we want to do performance monitoring, specifically for I/O, there is basically two different locations where we can insert the probe. So either we observe what's going on at the compute level. So within each compute node, the storage client, so the one in charge of transferring the data from the I/O from the compute node to the network to the storage server, will do some kind of characterization on statistics. And this is extremely fine grained, so it's cool because we know exactly what's going on within the compute node, so we can log in the node and see what's going on in terms of I/O. However, we are losing the big picture. So how are we able to assess what's going on within an application if the application is parallel and is spanning a large number of compute nodes? So if there is 100 compute nodes involved in the computation, then we need to extract this data from 100 nodes. It's quite complicated. So the other approach is to monitor the thing at the storage server side. So here this is centralized. So the server is receiving I/O requests from many compute nodes. And here we observe what's going on. We do statistics. And so we know exactly what is the total I/O bandwidth, for instance, delivered by the system. We know exactly what are the total level of metadata requirement. So it's very good. However, since everything is aggregated, it's difficult to sort out specific behavior. So typically, if there is few nodes exhibiting a very deviant I/O pattern, everything will be average on the server, and it will be difficult to know that these two specific compute nodes are actually stressing a lot the system. So these two observations push us to design the monitoring system in Evolve as a IP-based performance heat map. So it sounds a bit complicated, but let's say that the idea is that the client are going to tag all their performance data by their IP address. So performance data are not only going to be tagged by the time, so there is 1 gigabyte sent at time t, but also we concatenate to this IP address. On the server, we perform the consolidation using this IP address as a key. So now we will be able, from the server, we'll be able to retrieve exactly what's going on each compute node. So this idea seems simple, but in terms of implementation, so we had to implement several layers. So the most important one is at the bottom, at the client node. So it means the compute node. So the storage client, which is running on the compute node, is also capturing a lot of statistics. So it's not only performing the data movement to the network, but it's also taking a lot of stats. And these stats, then they are sent to the storage server. And the server is going to do the aggregation, so based on this IP address and timestamping. And out of this, we'll be able to build more meaningful statistics. We need first to send everything through a transportation layer. So in our case, this is Telegraph. So this is a software which is going to push the data out of the storage server in a reliable and efficient way to a database. So this is a storage part. So it's a time series database, InfluxDB, time series. So it's very convenient for performance data because each record is time-stamped, which makes sense when you want to do a performance observation. And ultimately, the database, we implement some queries, and the result of the queries are displayed in Grafana, which is nowadays, I would say, a kind of a standard UI. So in more detail, what do we have as a, I will say, a building block for our IP heat map? So this is displayed here in the screenshot. So you see that for the IP address 10.1.2.0, 101, we have the number of gigabyte during the last minute, so either in write and read. So basically we see that there is no data activity, so just few read operation. But we have the full list of metadata operation. Here we see that in the last minute, the node has exhibited, has made, pardon me, some metadata operation. So creating a directory, accessing some file, and so on. And so we can have this for every node connected to the storage server. So important point here is that each node knows also in which SLURM job is involved. So when SLURM is spanning an application on several nodes, is also setting some specific variable into the shell of the application. And the storage client is able to retrieve this information and send it to the storage server. So now the storage server is aware that this IP address 101 is basically belonging to the job 9942, and it can also aggregate to the same job all the IP address belonging to it. And so we can correlate the data. And here we do see some write activity. So previously the single IP node was not exhibiting a single write or a very few read. And here we see 10 gigabyte of write and 1 gigabyte on read. And we see also some metadata activity. So here we have an exact view of what's going on for a job, which is very important for HPC system. So at the client, there is also some advanced monitoring. So this is something that we are quite proud actually. So each client is able to record the histogram of the IO size. So we can know if this gigabyte of activity is a result of few very large IO requests or a lot of small IO requests. And in terms of performance, it has a very different impact for the storage system. So having access to this information is important in terms of performance tuning and optimization. So ultimately, all this information, they are queried, malax, if I can say this, and then displayed to a dashboard. So this is what we have currently for IME, so the flash system. So for each server, we know what is the capacity which is still available, what is currently the amount of write or read bandwidth, the number of metadata operation. We have the history for, I think, 15 minutes by default on the system. And at the bottom of this picture, you see a pie chart. And this is basically three most important jobs in the system. So we see that these three jobs are taking more or less the full bandwidth. No, to be correct, the full bandwidth is actually captured by only three jobs. But we can zoom into the job, and this is the additional rectangle that I've pasted on the top of this dashboard. And you see that for this SLURM job ID 75, we have a more precise vision of the IO activity. So interestingly enough, since we are using, I will say, almost standard components such as Grafana, this is very similar to what has been built for Lustre. So now for Evolve, even if we have heterogeneous storage, we have a kind of homogeneous dashboard, so we can monitor the same metric for a Lustre and IME. Of course, there is some system-specific metrics. So for example, here you see LNet. So LNet is a specific features from Lustre. But nevertheless, we can consolidate, I would say, a unified dashboard despite the heterogeneity of the system. So the wrap-up here, the only message that I want to convey today is that it works. So this heterogeneous storage system, it's working. So we are able to dispatch the IO workload on a per device basis. If we have fast NVMe, then they will receive more, a larger fraction of the workload than slow SSD, for instance. We have built this job characterization, so we can see what's going on the job basis in the system, which is, I think, critical for an HPC administrator. We have been able to capture and characterize the IO pattern at the client level, so we can build this histogram of IO requests. One important point here is that it's supported natively by the storage client, so there is no need to involve an additional profiling application. There is no need to do LD preloading or to introduce additional probe. The client is able to self-observe what's going on, and we can retrieve the data natively. So there is no additional storage involved here. And also, what I would like to mention is that despite the fact that our IME system is using single-ported device, so more affordable device, we have been able to ensure a very high level of data protection because we are using Erasure coding and an optimized Erasure coding library, actually. We still have, of course, some open issue or challenges. So we have accurate vision of what's going on at a job, but within the job, if there is a workflow which has been deployed into this job, we are not seeing what's going on a per container basis. So maybe this is something that we would like to add in the future. We have a very accurate vision of what's going on within the system, but we are not monitoring the input and output data channel from this system. So typically, if we download a large amount of data from the cloud to Evolve, we are not probing this. It's not integrated in our performance dashboard. And also, even if we are aggregating a lot of data, I think that we are still, there is still a lot of value which is not exploited. So we could do more aggressive classification, for instance, and this is still something which is open at the moment. So now it's time for me to let the stage to Per from MemoScale.
Yes. Thank you, Jean-Thomas. So let me see. Okay, so today I will talk about what MemoScale does in terms of data loss protection and transfer acceleration. So in large-scale storage systems, like the ones that are being used in Evolve, you need some kind of data loss protections because device failures, they are surprisingly common. And the more devices you have in a storage system, the higher the probability of some devices failing. And one of the most, obvious ways of protecting data against failures is to simply make copies of the data and then store those copies in separate locations. And then, of course, if one copy fails, then you can use the other ones to retrieve your data. And with a configuration like this, with 2 extra copies, you can tolerate 2 failures, which affects the same data. Erasure coding is a different technique for protecting data against loss. And a bit simplified, you could say that with erasure coding, you split the data into multiple fragments, like D1 to D4. And then you add some redundancy fragments, which are calculated based on the data. And you can use these redundancy fragments, R1 and R2, to recover any lost data fragments. So with this configuration, we have 2 redundancy fragments, and then we can recover from 2 failures. So there is one significant advantage to using erasure coding, and that is that it requires far less storage space. So here we can see that with these configurations, we use 50% less storage space with the erasure coding, and we can use even less if we use other types of configurations, like with more redundancy disks. So there is, however, one disadvantage with using erasure coding, and that is that it takes some time to calculate these 2 redundancy segments. And that's why we have developed an erasure coding library that's hand-tuned for multiple processor platforms. So we have tuned it to Intel, AMD, and ARM, and also PowerPC. And these are some benchmarks results where we measure the encoding speed with several libraries. So we have the Erasure library and the Intel ISA library. So both of those are open source. And for the first 3 columns here, we have done the test with using standard Reed-Solomon erasure code. And here we see that we are about twice as fast as the fastest alternative, the Intel ISA library. And we have also developed some special erasure codes, which are encoded a bit differently on the drives. And with this MemoScale CO code, we achieve about 3 times the performance of the Intel ISA library. In the Evolve project, the DDN's high-performance storage system called the IME is being used. And in this system, even the milliseconds counts in terms of for the latency. And DDN has integrated our erasure coding library and then measured the latency compared to the Intel ISA library. And here we see that we achieve about 11% reduced latency compared to the Intel ISA. So next, I will talk about storage acceleration or transfer acceleration. So data is not always stored at the same location where you are processing it. And in the Evolve project, data is transferred from many different locations. And when you transfer the data, it takes some time to transfer the data, and that can introduce some latency for the retrievals, and it could impact the workflow that you have, or impact the performance of the workflow that you are using. And also, these public cloud vendors, usually they charge a fee when you transfer data out of these clouds, and that's called the egress fees. So we have developed this transfer acceleration gateway to address these 2 challenges. And we call this transfer acceleration gateway S3AG in short. And it's a software that's installed using Docker containers on both sides of the connections, so both locally and at the remote location. And this software, it sits in the background, and then it compresses the data when you send it, and it decompresses it when you receive it. And from the user's perspective, you will use your S3 client, if you're using this on a S3 connection, the same way as before, because the software is completely transparent. But you will notice the effects of reduced increased throughput speed, but also reduced costs at AWS. So in the Evolve project, Sibeltech is a company that do some processing on satellite images on the Evolve platform, and they store their images at the AWS public cloud, and they download it to Evolve when they do the processing. So this is a very relevant benchmark for us to use when we test this software. So here we are done a test where we download a 836 megabyte large satellite image from AWS to the Evolve platform. And here we see that it takes about 360 seconds using a direct download with no acceleration. And when we use the MemoScale S3AG, it takes about 126 seconds. So that's about 66% reduced latency for that retrieval. And also, since we are using less bandwidth, we save costs. So you get about 64% reduced egress costs at Amazon. So to sum up, we get 64% egress cost savings, 66% reduced latency. I have to say that these numbers, they depend on how compressible your data is that you are sending. I can also mention that inside of this acceleration gateway, there is some advanced compression technology which adapts to the data type to some degree. And we have also developed this compression to perform especially well on numerical data and satellite images. There's also regulation technology, and this technology, it makes sure that the performance always increases, or in the worst case stays the same, but never decreases. And this means that you can have this acceleration gateway running in the background, regardless of what type of data you're sending. If there's an opportunity to improve the performance and reduce the cost, then this software will do it. Otherwise, it will not affect the performance negatively. So a last thing I can mention is that this accelerator gateway, it's fully compatible with the Datashim that IBM will present next. Thank you.
Sorry. Hi, Bert. So can I take over and
Yeah,
share the screen? All right, thank you. So morning to all of you. Thank you to John Thomas and Per for their talks. And John Thomas made a great point about heterogeneity in his introduction. And one of the things that we wanted to tackle in this project that is supported by Evolve is to deal with heterogeneity at a higher scale. And I'll speak about how Datashim presents a holistic approach to data access for analytics and machine learning on cloud. So we started off with the scenario where you have your data providers who are who manage data in big, large data lakes in enterprises, and they have data sets in these data lakes, and they have to configure access and enforce governance of these data sets. And on the other hand, the users or your data scientists just want to run their programs and run their analytics, and that involves searching through a catalog for data set information. Then the problem is that you could have a heterogeneous, the data lake could encompass a heterogeneous sources of data. So you could have data in databases, you could have data in object storage, you can have data in file systems. So there's an enormous amount of variety of storage systems for data. But from the point of view of the data scientist, she just wants to go on with their analytics. So, but she'll have to manage credentials, configure the jobs in Kubernetes to actually access the data set. And then you have to deal with the performance because each job will access the data, and access of data takes some time, especially if it's remote. So let me give you an example of what this happens in object storage. And why we picked up object storage is because it's the most popular solution for storing data in the cloud. It's cost effective, it's scalable, and entire companies and enterprises have stored their data on object storage, both for long term and for short term. And it's also very popular for analytics data, given the size of most analytics data and training data for machine learning. So, but when we on your right side, you can see that we have a graph of performance evaluation of training of ResNet 50, which is an image classification model using the ImageNet data using TensorFlow. And we did this with two GPUs with 4 nodes, two nodes with 2 GPUs, which means 4 GPUs. But the two GPUs, the GPUs that we use belong to 2 different families. So we had an older NVIDIA K80 on 2 nodes, and we had a newer NVIDIA P100 on 2 other nodes. And what you see here is that when we look at the performance where we where we measure performance as the time per epoch, which is the time that it takes for the training program to go through the data set one time. You can see that while with the older GPUs, they are almost consistent, and this is with direct access to data that was stored in remote object storage. The older GPU has a consistent performance, whereas with the newer GPU, you can see that there's a big drop when the data is stored on NFS versus when we access it from remote object storage. And that's because newer GPUs are faster, and so you're basically wasting expensive resources waiting for the data to arrive and get on with the job. So we wanted to, so this was a performance story. And while we were doing this, we also came across problems related to configuration that I mentioned before. You had to configure credentials, mount the data in a particular location. And so we wanted to have one approach that will basically solve these two problems together. And so we ended up with the Datashim project, and it started as a dataset lifecycle framework. Earlier this year, we were adopted by the Linux Foundation AI&Data Foundation as an incubator open source project. And with that, we also changed the name of the project to Datashim. And Datashim has it supports abstracts data access to Kubernetes by using a single Kubernetes object called Dataset. And the dataset is managed by an operator, which is a way in which you can write applications for Kubernetes. There's a framework called the operator framework, and this is managed by a dataset operator. And the dataset operator basically takes charge of making sure that we can access the dataset. It creates a mount points for the dataset, and it supports a consistent abstraction across multiple different storage backends, like, for example, object storage, which is S3, network file system, or H3, which came from the Evolve project. And by doing so, from the point of view of the user, she has just to have a reference to the dataset and put it on a Kubernetes cluster where Datashim is running, and then Datashim will take care of making sure that her jobs can access the dataset, or her pods can access the dataset. Now, because we have this abstraction, we saw that there were opportunities by which we could actually extend the abstraction to do a lot more than just ensuring single data access, which is we can, for example, solve the performance issue by introducing caches, right? And one of the things that we did was we developed a plugin based caching framework, and the plugin based caching framework we have right now, we have just an implementation for object storage, and I'll speak about it a bit, but it can be for any backend storage. We can introduce a caching framework. And because we know how the caches are configured, we can then use that information to actually get more performance out of the jobs by deploying the pods in a way that maximizes I/O access. So how do we do that? To go broader into the dataset object, we have the dataset operator, which manages the dataset objects. So on the left side, you can see an example of the YAML file that is used for defining a dataset object. And this is defining an object, a dataset that is stored inside a bucket called my bucket here in cloud object storage. We have to provide the access key and the secret access key, and you can also mask this by using Kubernetes credentials. You can provide an endpoint. The endpoint can be the endpoint of the service that offers the object storage service. And then what happens is that the dataset operator interfaces with the container storage interface driver that manages that backend. So in this case, it is CSI S3, which we also manage as part of our project. And the CSI driver then creates a pair of persistent volumes and persistent volume claims. The persistent volume is pointing to the backend bucket. The persistent volume claims is mounted by the pod. Now, and the pod can, and when there's an incoming pod, you just have to label the pod with the dataset ID and what is the mode in which you can use. And let's say the mode is mount, then the pod, then we change the pod to actually mount the dataset at the mount point that is requested. Sorry. And if you don't want to mount the dataset, then we have a mode in which we can actually export the information about the dataset as environment variables into the pod. And then, for example, if it's a job that requires direct access to S3 or object or cloud object storage, then we can then the program inside the pod can then go directly access that data. So now you can see how this will allow us to actually introduce caching because of the fact that all of this is abstracted to the workload running inside the pods. We can introduce the caching by just interjecting it between the CSI driver and the backend storage provider. So here there's an example of how we introduce a cache service and it's an inline cache for the storage provider. And all that changes is the endpoint. Once the cache service basically takes care of caching the storage provider and everything else, the rest of it goes as I described. Now the cache service, the interface to the cache service is managed by a cache controller. The cache controller differs per cache implementation. So we have a cache implementation, we have a control implementation for a cache that we based on Ceph that I'm going to describe next. And we are also working with Nuba, which is a multi-cloud gateway by Red Hat, and we will have an implementation of the cache controller for interfacing with their caching feature. So why did we have to create our own cache? So the first problem is that there is no caching for object storage that is inline. So we have different object storage in cluster object storage products from different companies, but there is no caching of object storage. And one of the things that we had to do was we had to have a cache to test out our work. So we took on Red Hat Ceph, and Red Hat Ceph is a storage solution from Red Hat that supports file, block, and object storage. And it supports object storage using a component known as Rados Gateway. And what we did, and Rados Gateway basically exports an endpoint that speaks object storage protocol or S3 protocol. So we extended Rados Gateway to reflect the contents of the remote bucket. So I don't want to go into the details of how we did that for time. But what we did was, practically speaking, everything in green is the stuff is the part of Rados Gateway that we extended. And what we have done here is that every time there was a cache miss error, we would actually fetch it from the remote bucket. We would reflect the local bucket to reflect the changes in the remote bucket and reflect the data that we fetched from the remote bucket. And then we serve the data to the requesting program, which in this case is a CSI driver. So there are different ways in which we could actually have this cache. So we could actually have a data backend, a distributed file system that is that then is available to a subset of the nodes inside a Kubernetes cluster, and the pods can then go mount the data that is inside this distributed file system, and the distributed file system then caches the cost-based bucket. And what I've shown is an example with the Rados gateway, is an example of the gateway mode, where the gateway is an S3 endpoint that exposes the data that is stored inside the data backend, and then all the pods talk to the gateway. Now, because we know the configuration of the cache, and Datashim is aware of that, we could now use this information to schedule the pods in a different way. Even without Datashim, you could actually schedule this pod. You could schedule pods that are cache aware by using a simple pod affinity, which is on the left side, a pod affinity term to actually schedule pods closer to the gateway. So here the idea being that pods that are closer to the gateway have the highest performance of data access. But what this will end up like, if you had pods that were belonging to a program like an analytics framework such as Spark or TensorFlow, you would end up with with an imbalance where some of the pods will actually end up being on the gateway or close to the gateway and having the best bandwidth, and some of the pods will end up being away from the gateway, and it will and these will have lower bandwidth. So you will end up having some sort of stragglers on these pods, whereas these pods will have faster tasks. So overall, the jobs that are running inside that framework will be slowed down. So to avoid this, what we have is we have a scoring method for pods that takes care that looks into the proximity of the nodes to the gateway, but it also takes into look but also it balances the load across the nodes that are part of the cluster. So this is more like a topology aware scoring. So here we check if the node is on the same topology as the gateway, or if the node is a gateway, and then we score the nodes, and then we add these scores to the other scores about the node availability and workload, and then we have much more balanced allocation. So this was developed with the API of the new Kubernetes scheduling framework. So it works in any scheduler that follows the scheduling framework, but we have tested this in Volcano and it works. So this supports things where you have like a group, so you have an all or nothing deployments like Spark or TensorFlow or even MPI, right? So our evaluation, we wanted to evaluate the caching and the data access abstraction. Now, in this case, we didn't use the scoring method. This was mostly static placements of pods because we wanted to test the impact of placement on the job performance. And here the benchmark that we used was the Transaction Processing Council Decision Support, or TPCDS benchmark, which its implementation was in Spark. We had 4 Spark executors that were running on 5 nodes inside IBM Kubernetes service. And in one of the configurations, we had them accessing data directly from object storage service, which is the IBM object storage service. In the second configuration, we had the gateway we had the cache, and the cache gateway was located on a node, and it was away from the executors. And the third one was a much more cache aware placement where the Spark executors were located in ways in which they can act. One of the Spark executors were located closer to the gateway, and so we wanted to see what would be the performance difference between these 2 configurations. And so, and here, just to be specific, the Spark access, the data was accessed by Spark through a mounted data point inside the pods. So the performance is, I mean, pretty much when you add the cache, obviously you're going to get a speed up in the overall execution time of TPCDS. TPCDS consists of 99 queries. I forgot to mention that in the previous slide that we have 300 gigabytes of data that were compressed to 100 gigabytes, and so we had pretty much like more than half improvement in the performance by using the cache. But the interesting thing is that by using the placement, we found that we could actually improve the performance by even a 10% over the cache alone, right? And this means that placement actually matters, and this is something that we want to use in our in the scheduling that we'll do for the pods when Datashim is involved in getting the data. Now, on the if you go on a per query basis, we have some of the most worst performing queries when you use direct access to cause. So these are the top 10 of them, and you can see that when we look at the top 10 performance improvements, or the queries that had the best improvements in performance, you can see that the same pattern is being reflected. You have the best improvements for the queries that scan through the entire database. Like these ones are all reporting queries that actually scan the entire database and generate reports. And again, the placement matters because we found that you can have actually different placements actually produce better performance, right? So with that, I would like to conclude. So what I've shown is that Datashim provides a Kubernetes native data access abstraction for managing configuration, and it provides a plugin-based caching of data sets to manage performance. So we managed to tackle these two issues together in a single holistic framework, and that's basically what our selling point is, right? And what we have, and this works across heterogeneous data sources. So this ties in with the evolve ambition to manage heterogeneity inside cloud infrastructure. We demonstrate that placement of pods. We have demonstrated that placement of pods impact work performance of workflows, and this will be reflected in our ongoing work, which is how to come out with a cache-aware Kubernetes scheduler plugin that works with any Kubernetes batch scheduler. We are also now doing a further analysis of cache I/O on Kubernetes workloads, and we are finding some interesting implications that will tell us how to scale gateways for caches in the future. And we could use that for actually driving optimization of caches when multiple workloads are running on a multi-tenant cluster. So with that, I would like to conclude this talk. I'll hand this over to Jean-Thomas to end the webinar. And we are happy to take any questions, of course.
Thanks a lot. So let's go to the. No, I think we are reaching the last part of the webinar. So let's see if we have a question to address. Let me move this way. Yes. So do we have any question?
No.
Okay. So this is because we have been super clear, for sure. Anyway, there is more technical talk schedule. So if you're interested in more webinars about what has been developed, test, implement in Evolve, please check the loba.com, webinar.loba.com/evolve. So you will find the previous material, and also this will be the place where the coming webinar will be archived as well. And our next webinar in Evolve is about automotive and mobility service. So it will be in 1 week from now, same time. And I wish you all a very good day, and thanks for your attendance. Bye.
Thank you very much.
Thank you. Bye.